Hello everyone and welcome to Pre-Calculus Algebra Lecture 15 Part 3. I've done this a little out of sequence. I did Lecture 16 Part 1 the other day, but I realized afterwards that I needed to do some material before Lecture 16 Part 1. So I'm doing Lecture 15 Part 3, and this is the last of the Lecture 15 series. We're going to graph polynomials today, and with maybe a few minor changes, we're going to follow the outline that's in our text. If we have a polynomial, the first thing that they suggest is to factor the polynomial if it's in expanded form. If the polynomial is in expanded form, if the polynomial is in factored form, expand it. If the polynomial is in expanded form, factor it, just so that we have both ways of looking at the polynomial. The next step, find all of the real zeros and their multiplicities. Then find the intercepts, and that's very closely related to the real zeros. Remember that the x-intercepts, those are the real zeros. Next, we're going to consider turning points, the maximum number of turning points that we can have, and also whether we're going to have an even number or an odd number of turning points. And then finally, we'll consider the end behavior. This is our approach to graphing polynomials. We're going to do all of these things pretty much in that order, and then we're going to graph the son of a gun. Here's our first example. F of x equals 4x cubed plus 10x squared minus 4x minus 10. And this polynomial is in expanded form or standard form. And so what we want to do is factor this thing. That's the first thing that we want to do. I see two ways that we can go about doing this. And I'm going to do this both ways because if we're faced with a polynomial like this and we need to factor it, we may not see one way right away, but the other way may work just fine. So here's what I'm going to do it both ways. The first way, I'm going to factor it the way that we've been taught to factor things. And something that jumps out at me is that I see 4, 10, negative 4, negative 10. This tells me that somehow I can group these two together and group those two together. And that is going to help me factor this polynomial somehow. So I'm going to take these two. I see 4, 10, and I see essentially 4, 10 here. So I'm going to group these two terms together and these two terms together and see if that gives me any further insight. Okay, perfect. From this group, I'm going to remove a common factor. And I see that, well, let's see. I see that both terms have a factor of 2. And I see that both terms have a factor of x squared. So 2x squared is the factor that I'm going to remove. If I remove 2x squared from this term, that leaves me with 2x. If I remove 2x squared from this term, that leaves me with 5. 5 times 2x squared is 10x squared. That looks good. 2x times 2x squared is 4x cubed. That looks good. Now I'm going to do the same thing with this pair of terms. Do they have any common factors? They do. They both have a factor of 2. So I'm going to remove that common factor. And that will leave me with 2x plus 5. And once I've done this, I look at the two terms that I have here and here, and I say, son of a gun, these two terms have a common factor, 2x plus 5. So I'm going to remove this factor from both terms. Excuse me for just a minute. My marker just died. Let's see if this one will serve more admirably. If I remove the factor 2x plus 5 from both of these terms, if I remove it from the first term, I have 2x squared. If I remove it from the second term, I have 2. And I guess technically, I can do a little better than that. I can remove a common factor of 2 here, can't I? Holy moly. You know what? I'm still not done. Because I'm looking at this now and I say, aha, this is the difference of perfect squares. So I'll get x plus 1. I'll get x minus 1. And then here I have 2x plus 5. Okay, now that is factored. And I will write this result up at the top. This is 2x plus 1, x minus 1, 2x plus 5. Now, I did say that there was another way to factor this. When looking at this polynomial, it just might not have clicked. Hey, 4, 10, 4, 10. It just may not have. It didn't hit me at first. And sometimes we just don't see things that are right in front of us. So let's look at alternative method for factoring this polynomial. Here's my alternative method. I have a polynomial that I want to factor. I'm going to look for whole number factors of the constant term. Here's the constant term, -10. I'm going to look for whole number factors of this constant term, which make f of x equal to 0 when we plug in those numbers. So, the factors of -10 are plus or minus 1, plus or minus 2, plus or minus 5. Let's see what happens. If I plug in 1, x equal 1, I get 4 plus 10 is 14, minus 4 is 10, minus 10 is 0. We hit the jackpot on the first try. F evaluated at 1 is 0. So what's the big deal? The number that we plug into f of x to make f of x 0, that's 1, is such that x minus that number is a factor. F of 1 equals 0, f evaluated at 1 equals 0. So x minus 1 is a factor of f of x. Son of a gun. Talk about luck. We plugged in the first factor and we got 0. Let's see if we can get some more factors. Let's see, the factors of -10 are plus or minus 1, plus or minus 2, plus or minus 5. Let's see. We plugged in 1. Let's plug in -1 and see what happens. If we plug in -1, we get -4 plus 10 minus a -4 is plus 4. Let me write this down. What the heck? I'll write it out. F evaluated at -1 is 4 times -1 cubed plus 10 times -1 squared minus 4 times -1 minus 10. If we cube -1, we get -1. So this is -4. If we square -1, we get +1. So this is plus 10. -4 times -1 is plus 4. And we have -10. And son of a gun, you know, we are lucky today. We usually don't get this lucky this quickly. We hit the jackpot again. We have -4 plus 4 is 0. Plus 10 minus 10 is 0. If I plug -1 into the function, I get 0. F evaluated at -1 is 0. This means that x minus x x minus this number, so x minus a negative 1, is a factor of f of x. Now that we've done that, let's simplify this. X minus a minus 1, well, that's just x plus 1. So we have another factor. Son of a gun. We have x minus 1, we have x plus 1, and let's just try the other factors of 10. If we plug in 2, we're going to get 2 cubed is 8 times 4 is 32. 2 squared is 4 times 10 is 40. 4 times 2 is negative 8 minus 10. So we have 72 minus 8 is 64 minus 10 is 54. We plugged in 2, we didn't get 0. So nothing special about x equal 2 here. Let's plug in negative 2. Negative 2 cubed is negative 8 times 4 is negative 32. Negative 2 squared is plus 4 times 10 is 40. Negative 4 times negative 2 is plus 8 minus 10. Well, let's see. Negative 32 and minus 10 is negative 42. 40 plus 8 is plus 48. So we have plus 48 minus 42 is 6. We plug in negative 2, we get 6. We don't get 0. So there's nothing special about x equal negative 2 either. And oh my goodness, if we plug in 5, we get some really big numbers. 5 cubed is 125 times 4 is 500. 5 squared is 25 times 10 is 250. 5 times negative 4 is negative 20 minus 10. We plug in 5, we get 750 minus 30 is 720. Well, that's sure not 0. So there's nothing special about the factor 5. Let's try negative 5. Negative 5 cubed is negative 125 times 4, negative 500. Negative 5 squared is 25 times 10 is plus 250. Negative 5 times negative 4 is plus 20 minus 10. Okay, let's see. Negative 500 plus 250 is negative 250. Plus 20 is negative 230. Minus 10 is negative 240. We plug in negative 5, we get negative 240. That's definitely not 0 either. Okay. We've plugged in all of the whole number factors of negative 10. And that helped us get 2 factors of f of x. The third factor we're going to kind of sort of have to figure out on our own. Okay, here's where we do some detective work to get the remaining factor or factors. F of x, 4x cubed plus 10x squared minus 4x minus 10 is equal to x minus 1 times x plus 1 times some mystery factor that we haven't figured out yet. But we're going to figure out what factor goes here right now. And here's how we do it. What we have is a third degree polynomial, x cubed. We have x times x is x squared. So whatever goes here has to be something times x. X times x is x squared times something times x gives us 4x cubed. X times x is x squared. X squared times what gives us 4x cubed? X squared times 4x gives us 4x cubed. Is that right? X squared times 4x is 4x cubed. So 4x is what goes here. Now, whatever goes here is going to be a constant term. And it has to be such that when we take this number, 1 times minus 1, and multiply it by this number, we get negative 10. 1 times minus 1 is negative 1, times whatever goes here is minus 10. Well, minus 1 times what gives us minus 10? Isn't that 10? 1 times negative 1 is negative 1, times 10 is negative 10. There's our missing factor. And we look at this and we can take out a common factor of 2, right? And have 2x plus 5, x minus 1, x plus 1, and voila. We got our polynomial in factored form. And this is a handy way of doing it if we didn't see the grouping trick that we used as an alternative to start off with. But one way or another, we have our polynomial in factored form. Beautiful. Next thing we're going to do is look at our real zeros. Next thing on the agenda, find the real zeros of our polynomial and their multiplicities. And the best way to do this is just to take the factored form of f of x and set it to 0 and solve for x. So we'll take the factored form of f of x, set it to 0, and solve for x. If we have a product that's equal to 0, one of those factors must be 0. And it sure can't be this one. This is always equal to 2. But x plus 1 could equal 0. Or x minus 1 could equal 0. Or 2x plus 5 could equal 0. And in this case, this tells us that x equals negative 1, or x equals positive 1, or 2x equals negative 5, which means that if we divide both sides by 2, x equals negative 5 halves. Those are our real zeros. And notice that each of these factors is raised to the power of 1. Each of these factors is raised to the power of 1. So the multiplicities are all 1. That's going to tell us something about our x-intercepts. And I guess I won't mention that right now, but these are our real roots. They all have multiplicity of 1. And in the next step, when we talk about our intercepts, the multiplicity, in particular, the fact that the multiplicity is an odd number, is going to be important. Next step, find the intercepts. And we have the x-intercepts already. X equals negative 5/5, x equals negative 1, x equals positive 1. And all of these intercepts have multiplicity of 1. The key here is that the multiplicity of each of these is an odd number. And since the multiplicity is odd, at each x-intercept, the graph of f of x crosses the x-axis. But we want to remember that. At each x-intercept, the graph of f of x is going to cross the x-axis. So here's the x-intercept right there, and the graph is going to cross from one side of the x-axis to the other. That's what always happens if the multiplicity of a real zero or an x-intercept is odd. If an x-intercept has multiplicity that's even, the graph doesn't cross the x-axis. It kisses the x-axis right here at the x-intercept, and then it turns around and goes back. So if the multiplicity is even, the graph doesn't cross the x-axis. If the multiplicity is odd, the graph does cross the x-axis. And that's why we made a big deal about the multiplicity. The key is the multiplicity even or is it odd? If the multiplicity is odd, the graph's going to look like this at the x-intercept. If the multiplicity is even, the graph's either going to look like this or it's going to look like that. The graph will touch the x-axis, but it won't cross if the multiplicity is even. To find the y-intercept, we set x equal to 0, and we do that using the expanded or standard form of the polynomial. F of 0 equals 4 0 cubed plus 10 0 squared minus 4 times 0 minus 10, 0, 0, 0, minus 10. That's the y-intercept. So the point negative 10 on the y-axis is the y-intercept. Turning points, where the graph changes direction from going up to going down, or where the graph changes direction from going down to going up. Turning point, turning point. And here's how we address that. We look at the degree of the polynomial. F of x has degree 3. So f of x has at most the degree of the polynomial minus 1 our polynomial has at most 2 turning points. Also, our polynomial is of odd degree, so f must have an even number of turning points. So either f of x has 2 turning points or 0. Those are the only possibilities. Those are the only even numbers that could be the number of turning points of f of x. And finally, end behavior. The last thing we'll consider is the end behavior. F of x the leading term of f of x, the term of highest degree, is 4x cubed. Therefore, if we encapsulate the intercepts and turning points in a box, so we're going to take all of our intercepts and all of our turning points and we're going to encapsulate them in some sort of black box. The graph of f of x looks like the graph of f of x equals 4x cubed, the leading term, outside of the black box. F of x equals 4x cubed. Remember our old friends, -1, 0, +1. And when x equals -1, 4x cubed is -4. When x is 0, f of x is 0. And when x equals 1, f of x equals +4. So outside of the black box that we have here, the graph of f of x pretty much behaves the same way as the graph of 4x cubed. So our function is going to look like this outside of the black box. And what the function looks like outside of this box is what our authors call end behavior. So the bottom line is f of x behaves like 4x cubed. Okay, we've milked this for all it's worth. Let's graph. Okay, let's graph this son of a gun. F of x equals 4x cubed plus 10x squared minus 4x minus 10. And the x-intercepts, x equals negative 5/2, so that's 1 right there. X equals negative 1, there's another. X equals positive 1, that's the last one. They all have multiplicity of 1, which means the graph crosses the x-axis at each x-intercept. The y-intercept is negative 10, way the heck down here. And we either have 2 turning points or no turning points. And something else. F of x behaves like 4x cubed, so eventually it's going to go up like this, and to the left of the origin it's going to go down like that. Now let's see if we can make sense of this. Right here we have a point in between our 2 x-intercepts. So the graph has to come down here, go through negative 10, and come back up here through negative 1. And remember we said our x-intercepts have multiplicity of 1, and that means the graph has to cross the x-axis at each intercept. So not only does the graph touch the x-axis here, but it has to keep on going like this. And over here, the graph has to go through this point. So between here and here, the graph has to turn around. And go through the x-axis. Now, we had 2 turning points. We got a turning point right here. We got a turning point right there. Maximum number of turning points is 2. 1, 2. We ain't got no more. The most we can have is 2 turning points, and here they are. Which means that over here, the graph has to keep on going in this direction. It can't turn around and come back. Which is fine because according to the end behavior, the graph has to go down and to the left, just like the graph of 4x cubed. And over here, the graph can't turn around and come back because that would be a 3rd turning point, and we only got 2. So this graph has to keep on going up and to the right like that. Which is fine because this is what our end behavior tells us the graph should look like. It should go up and to the right, just like the graph of 4x cubed. And there's our graph, suitable for framing. Hey everyone, we're factoring polynomials. And I got this one out of our book. It looked like a good one. Graph this polynomial. So our first step is either to expand or to factor. And I thought the people that wrote our book were my friends, but now I'm beginning to think that maybe they're not, because you see the way they gave us this polynomial? It's definitely not in expanded or standard form. And now that I look at this a little bit more closely, it's not in factored form either, because I look at this thing and I go, son of a gun. Difference of perfect squares. This thing can be factored. So for my step 0, I'm going to have to factor this thing, and I'm going to have to expand it. My friends who wrote the text didn't really do either one. So the first thing I'm going to do is factor it. And this thing, it just jumps right out at me and says, factor me, factor me. X plus 4, x minus 4. See, this is x squared minus 4 squared. And you know what? Maybe I should write that as an intermediate step. X squared minus 4 squared. Yeah. And now I know I can see. It's the difference of perfect squares, so it's going to be x plus 4 times x minus 4. Okay, much better, much better. Next thing we're going to do is expand this and write it in standard form. I'm going to expand this thing and write it in factored form. And I think my first order of business is to multiply that out. X minus 1 squared. I get the first thing squared. I get the second thing squared. And I get the first times the second thing doubled. X times minus 1 is negative x, and I double that, I get minus 2x. Okay. X squared times x squared is x to the 4th. X squared times negative 16 is negative 16x squared. Negative 2x times x squared is negative 2x cubed. Negative 2x times negative 16 is plus 32x. And 1 times x squared is x squared. 1 times negative 16 is negative 16. And now I'll just add all of this garbage up. X to the 4th minus 2x cubed minus 15x squared minus 32x minus 16. And you know, before I added all of those up, I should have checked these to make sure I got them right. X squared is x to the 4th. X squared negative 16x squared. negative 2x times x squared, negative 2x cubed. Negative 2x times negative 16 is plus 32x. Okay, I'm looking good. For the first time in my life, I am looking good. And finally, I'll just distribute the negative 2 inside the parentheses. Negative 2x to the fourth plus 4x cubed plus 30x squared minus 64x plus 32. And let me just go over this carefully. I think that's right. Okay. So now I have f of x in expanded or standard form. My next order of business is to look at real zeros and their multiplicities. Our next order of business, look at the real zeros and the multiplicities. And to get our real zeros, we want to consider the factored form of f of x. So here's our factored form. Negative 2x minus 1 squared, x plus 4, x minus 4. That we set f of x to 0. And we realize that we have a product that's equal to 0. That can only happen if one of the factors is 0. And it ain't going to be this one. Negative 2 can't be 0. But x minus 1 can be 0. So let's see, x minus 1 could be 0. Or it could be the case that x plus 4 is equal to 0. Or it could be the case that x minus 4 is 0. And this tells us x equals 1. Or x equals negative 4. Or it tells us that x equals plus 4. Those are our real zeros. X equal 1. And notice where this came from. X equal 1 comes from the factor x minus 1 squared. See that right there? That exponent? Multiplicity 2. X equal negative 4. And x equal positive 4. Both of these have multiplicity 1. Now, what does that mean? For future reference, when the graph of f of x intersects the x-axis at x equal 1, the graph is going to touch the x-axis, but it won't cross the x-axis. The graph will touch the x-axis at x equal 1 and it will turn around. So that means that we also have a turning point here for future reference. We have a turning point at x equal 1. Over here, the multiplicity is 1. It's an odd multiplicity, which means that the graph crosses the x-axis at x equal -4. The graph crosses the x-axis at x equal +4. We look at our intercepts now, and our x-intercepts are the same as our real zeros. So x equal -4 and x equal +4 are x-intercepts. X equal 1 is an x-intercept. And I'm noting here that at x equal 4, the graph crosses the x-axis. At x equal +4, the graph crosses the x-axis. At x equals 0, the graph doesn't cross the x-axis. Instead, I'm going to write here TP for turning point. Those are my x-intercepts. What about my y-intercepts? We'll set f of x equal to 0. And I'm going to use the expanded form here. And you know what? That's not what I want to do for my y-intercept. My brain was on autopilot. For my y-intercept, I want to evaluate f of x at x equals 0. So what I'm going to do is I'm going to plug 0 into f of x, and I'm going to use the expanded or standard form. -2 times 0 to the 4th plus 4 times 0 cubed plus 30 times 0 squared minus 64 times 0 plus 32 is 32. So when x is 0, y is 32. That is our y-intercept. Next on our agenda, turning points. And we want to know the maximum number of turning points and the possible numbers that we could have. Notice that f of x is of degree 4. That's important. F of x is of degree 4. Hence, f of x can have at most 4 minus 1, the degree of the polynomial minus 1, turning points. So we can have at most 3 turning points. F of x is of even degree 4. So f of x must have an odd number of turning points. So either f of x has 3 turning points, or f of x has one turning point. Those are the possibilities. And we know we do have a turning point at x equal 1. Now the question is, do we have two more, or is x equal 1 the only turning point? I guess we'll have to wait just a little bit longer to answer that question. One last thing to consider, the end behavior. And we notice that the leading term of f of x is negative 2x to the fourth. What that means is that outside of the box, and this box that I'm talking about is a box that encapsulates the intercepts and the turning points. We take the intercepts and the turning points and encapsulate them in a box. And outside of that box, the graph of f of x is going to look like the graph of negative 2x to the fourth. That's what that means. And what does f of x equal negative 2x to the fourth look like? Well, let's say that we have our old friends, negative 1, 0, and positive 1. And at x equal negative 1, x to the fourth is positive 1 times negative 2. So when x is negative 1, whoops, I sure messed this up. Pay no attention to that man behind the curtain. Negative 1. Yep, negative 1 and 1 are still our old friends. But, yeah, our leading coefficient is negative. That means the graph is going to open up downward. When x is negative 1, f of x is negative 1 to the fourth, which is positive 1, times negative 2 is negative 2. So negative 1, negative 2 is a point on the graph. When x is 0, f of x is 0. When x is 1, f of x is negative 2 times 1 to the fourth, which is negative 2. Whoops, positive 1. So those 3 points form the skeleton on which we hang the graph of f of x equals x to the negative 2/4. And what that means for the graph of the function, this thing, negative 2x, f of x equals negative 2x to the fourth plus 4x cubed plus 30x squared minus 64x plus 32, blah, blah, blah. What that means is, if we encapsulate the intercepts and the turning points outside of this box that contains the intercepts and the turning points, the graph of this function looks like the graph of negative 2x to the fourth. So outside of the box, our graph is going to do this. And we call this the end behavior, or our author calls it the end behavior of our function. So the end behavior outside of our box, this is what the graph of our function is going to look like. Let's graph this thing. I have a rather unusual scale for the graph. Our x-intercepts lie between negative 4 and positive 4. So I have negative 4 and positive 4 be increment markings on the graph. The y-axis, I definitely have a different scale for the y-axis because The y-intercept is positive 32. Somehow we've got to be able to get the point y equals 32 on this graph. As a matter of fact, why don't we just put it there? There's y equal 32, just a little bit above y equal 30. So we graphed our y-intercept. Our x-intercepts are negative 4, positive 1, and positive 4. Excellent. Let's see, what else do I know? X equal 1, it's an intercept. It's also a real 0 with multiplicity 2. The graph is not going to cross the x-axis at this point. The graph is going to turn. X equal 1 is a turning point. So from here, the graph comes down and it kisses the x-axis right here at x equal negative 1, but it doesn't cross. It kisses the axis right here at x equal negative 1 and changes direction and goes back up. Well, the graph of f of x has to go through this point too. It's another x-intercept. How is the graph going to get from here to here? It's got to turn around, doesn't it? So we're going to have another turning point somewhere between x equal 1 and x equal 4. And we have a point on the graph right here at y equal 32 on the y-axis. And on the x-axis, we have another x-intercept. So the graph has to go from here to here. How is that possible unless somewhere between here and here the graph turns around? The graph's going up here, but in order to get to this point on the x-axis, it has to turn around, doesn't it? So somewhere between the origin and x equal negative 4, the graph turns around. And it crosses the x-axis. At x equal negative 4, the graph crosses. At x equal positive 4, the graph crosses. Now, what have we taken into consideration here? We've taken into consideration the real zeros, which are also the x-intercepts. We've plotted the y-intercepts. And turning points, let's see, we have a turning point here, we have a turning point here, we have a turning point here. 3 is the maximum number of turning points that we can have. And 1, 2, 3, we got 3 turning points. There ain't gonna be no more. Which means that the graph can't turn around. It has, right here, the graph can't turn around. It has to keep on going down and to the right. And right here, the graph can't turn around. It's got to keep on going down and to the left. And you know what? This part of the graph and this part of the graph agree with our end behavior. A little bit earlier, we said this is what the graph of f of x is going to look like. If we encapsulate our intercepts and turning points and put them in a box, outside of the box, this is what the graph is going to look like. It's going to go down and to the left, which this does, and it's going to go down and to the right over here, which it does. What that means is that we have graphed this thing to perfection. So let me erase everything except the definitions of f of x. Voila, we have graphed it. And a nice looking graph it is too.